I'm very pleased to be here today to speak about a topic which may be a little bit different about some of the other topics treated earlier, in that we're not so much talking about how we protect the space segment, but how we use the space segment to provide a service, a cryptographic service. And if I go into a little bit more detail, specifically a service that's using quantum technology. Now in Airbus, we're very active in several areas of quantum technology, in both quantum computing, quantum sensing, and quantum communication. And this is because it's seen as a transverse topic. That means a topic which is useful for all of our divisions. So you can well imagine that quantum computation of computational fluid dynamics is useful for any flying vehicle, and similarly enhanced navigation using quantum sensors is also good for any division which has flying vehicles. But today I'll be speaking about quantum communication. So there's two main threads to this topic. There's the topic of quantum information networks, where we want to provide the infrastructure to allow quantum sensors and quantum computers to be linked together. So quantum information networks. But more specifically today, I'll be particularly addressing quantum cryptography, where we want to provide cryptographic solutions which can respond to the threat of quantum computers to cryptography, as has been discussed earlier in the context of post-quantum cryptography. But unlike post-quantum cryptography, which is an algorithmic solution, here we provide a solution based on quantum physics, where we actually use the laws of quantum physics to provide a guaranteed security of the key. And Airbus is not the only entity which is enthusiastic about quantum technologies. We're very fortunate in Europe to also have several agencies who are also believe in this for the future. So the topic is very strongly supported by the European Commission and ESA, European Space Agency. And we've been working in very close collaboration with these two entities throughout the years, having led several major architectural studies over the years for both terrestrial systems and space systems. And one of the pillars of this strategy for the European Commission is to put into place something called the EuroQCI, the European Quantum Communication Infrastructure, which the role is to provide end-to-end secure, quantum-secured keys, with an evolution in the future to going more towards this other topic of quantum information networks. So it's very much a forward-looking project. The initial clients of such a service would be the governmental infrastructure in Europe, but eventually other use cases would be found in much the same way as once infrastructure is in place, such as the ARPANET later gave birth to the internet as we know it today. Now, I'll just give a little reminder of what quantum key distribution is, but I'll only explain it on a functional level. If we were to go into the details, that would take us far too far away from the topic of this conference. But its functional role is to provide a shared key between two users. So these users are Alice and Bob, and the shared key is this KAB. And to do so, the important property about this shared key, and this is why we do this, is that it's an ITS, information theoretically secured key. The generation of this key does not rely on any conjectures about computational complexity. And to do so, we need to have a quantum channel, a channel where we can transmit individual quantum particles, and in doing so, by transmitting individual photons, in this case, individual particles of light, and we encode information on the polarization of these photons. And the specific property that's useful for this application is that any measurement of these photons will perturb them. And this is a physical law. This is Heisenberg's uncertainty principle. And similarly, there are laws that prevent you from duplicating any of these photons and just measuring the copy that you've made. So that's called the non-cloning theory. So we have this channel of very sensitive particles, and we can detect any intrusion on it. And the other ingredient that we need in this is a parallel classical channel, an authenticated classical channel, in order to prevent against man-in-the-middle attacks. And the important thing about this quantum channel is it can't just be any old channel. It needs to be already a channel that is capable of transmitting optical communications, and a rather clean channel. We need a very good signal-to-noise ratio because we're transmitting individual photons. We need to identify them against background noise, and we don't have the right to amplify the signal. This would violate the no cloning principle that I mentioned earlier. So the protocol that I mentioned here is called the prepare and measure protocol, and we have one of the users prepares states randomly and the other one measures them randomly, and then through a process of post-processing and communication between the two parties, a key is established. But there is an alternative protocol with a slightly different geometry, and this is called the entanglement-based protocol. And in this case, Alice and Bob are both receivers. They have the same role in this protocol, and there's a source of entanglement in the middle. And I won't explain exactly what entanglement is, but for today, it suffices to say entanglement is a source of correlation. So the states that are transmitted to Alice and Bob are correlated. But what is very specific about entanglement, this correlation is established at the moment that one of the parties performs the measurement. And this property means that we can use this correlation, of course, to generate a key, but we can also use this particular property to identify if any measurement has been performed before arriving. So if we had an intruder, Eve, trying to make a measurement, we would also detect that here. And likewise, if the supplier of the source was tampering with it and trying to measure it, we could also detect that. So in this respect, we say that entanglement-based QKD, we don't need to trust the source. So this is an untrusted protocol, which is a good thing. And how these two protocols end up being implemented in a space segment is something like this. So on the left-hand side, we see the prepare and measure protocol that I showed at the beginning. And on the right-hand side, the entanglement-based protocol. So what we see with the prepare and measure, we would have the source mounted aboard the satellite. It's easier to perform downlink operations and have the rather complicated single photon detector on the ground. We need to have a parallel classical channel. And in this, we establish a key between the satellite and the terminal, which is clearly not the service we want to provide. We want to provide a service where we provide a key between two users on the ground. So I'll shortly describe how we achieve that. But I can, for now, just mention that there's a very specific advantage of this approach, is that we can provide a relatively higher key rate than that's what's achieved from the entanglement-based protocol. The entanglement-based protocol, as I mentioned earlier, has this very distinctive advantage of not having to trust the satellite infrastructure. This means that there's less need to provide secure guarantees about all the supply chain, and it also means that the service can be provided to users that do not know Airbus products, or they don't need to trust us, that they can still use the service. Unfortunately, this approach does have a disadvantage. It provides a considerably lower key rate. And another disadvantage is that, of course, the satellite needs to be simultaneously mutually visible to these two users here, because they need to both receive a photon from the satellite. Incidentally, the reason for this lower key rate is related to this. Successful communication is achieved when a photon arrives successfully to A and also to B. So the probability of success is the product of the probability of an arrival at each one of the two. So this is certainly much lower. And also given the fact that we need to have two optical terminals which form these beams of photons and send them to the ground. These two terminals mounted on the satellite are typically then smaller than the single optical terminal that we can have for prepare and measure. So all these factors conspire against us to have a key rate, which is as strong for entanglement-based as it is for prepare and measure. But there is also a further advantage of this approach, is that this is compatible with this future quantum information network that I spoke about earlier, because quantum information networks employ a process called quantum teleportation, which sounds very exotic, but is something that's been demonstrated multiple times in the laboratory and in the field to transmit qubits from one end of a network to the other. So I'll just go back to say how we can use this prepare and measure approach to actually establish a key between two users on the ground. So the way we go about it is, firstly, this is a similar image to before, with the satellite, which would typically be in a LEO orbit, progresses along its way, and in an opportunistic fashion, depending upon the weather predictions, the demand from users for keys, and the available stations on the ground, a key is generated between a station A and the satellite. So that's the KAS. The satellite progresses along its orbit, and then in a similar fashion, when there's an opportunity, it will generate a second key with the ground station B. So that's the key KBS. So now the satellite has keys shared with both these parties on the ground, and what the satellite can then do at a later time or instantaneously is to encrypt one of the keys with the other one, and this must be done, of course, using an ITS protocol, such as the one-time pad, as is shown here, where you just take an XOR of one of the keys with the other one, and then this can be broadcast, and theoretically you preserve confidentiality even if you broadcast this over a public channel. That could be over an RF channel or any other means you wish, and it would still preserve confidentiality of the communications. So now Alice can receive the XOR of this key, and she's then able to decrypt it, once again using the one-time pad procedure, and she now knows KBS, which Bob already possessed. So now they have a shared key, and they need to throw away the KAS, of course. That can't be reused. But what we do see, two things. We see that Bob doesn't need to be close to Alice in this scheme. Bob can be the other side of the world, and this would still work. So this allows a global distribution of keys, and indeed distance is not penalized. We also see that this is not a time-dependent system. This is more a system which delivers keys over the long term. And so a Euro QCI would look something like this. You have a terrestrial segment which plays to the strengths of higher key rate, but there's a distance limitation due to the intrinsic loss mechanisms inside fibers. So typically, the terrestrial component can't reach distances much greater than 100 kilometers. And this is where a space component kicks in, and Airbus group is working as a prime on the space segment, and also some of the key technologies in network control and management for the terrestrial segment. Now I make a little mention of, as a system prime, how we go about developing such a system, because we need to have a very faithful end-to-end model of how key generation and key distribution works. And of course, these models need to be developed in-house. So we've spent quite a lot of effort developing software to do this work. And we've developed a time domain model where we follow the satellites along their orbits, and we calculate the channel, and we take into account several physical phenomena for the channel. So not only we have the atmospheric absorption, we replay real-time cloud data using measured data, global data. We also take into account telescope pointing errors, because for a very fine beam of telescopes, any offset is very important. And perhaps most delicate of all is that of atmospheric turbulence and its correction using a method called adaptive optics. So this models the attenuation. We also have very detailed models of noise sources, because this is just as in classical communications, it's about signal to noise in the end, and other atmospheric impairments. And we plug this into our model of the QKD post-processing, which actually tells us how much key is generated for a given signal to noise. And then once we have that, we need to decide what's the best way of exploiting the satellite as it goes along its orbit. And so this is where mission planning algorithms are used. So we use optimization methods, which we draw on the extensive knowledge of our teams who've worked on Earth observation, because this is a very similar problem to Earth observation in the end. So there's already algorithms in place that allow us to do that in an optimal fashion. And that allows us to calculate how optimally to generate the key and then to distribute it to the end users depending on the demands that were made at the beginning of the mission. So all told, when we put all these factors together, there's quite a significant degradation compared with the maximum key that could be generated from a satellite at zenith, and to that which is encountered in an end-to-end fashion when we've taken into account the fact that the satellite will sometimes be over the oceans, and that we won't deliver key when it's not requested by an end user and things like that. The end-to-end capacity is typically 5% of what it would be maximally for a satellite at zenith. Here we see the algorithm in action. And so this lets you know what it feels like to be a QKD satellite. You spend your life orbiting the Earth and prioritizing connections with sites depending on the cloud cover, which is shown in red, and also the store of keys that have already been established with these individual sites. And then when you arrive at areas such as the oceans, this is also useful. You can replenish the batteries of the satellite. So I mentioned earlier that the end-to-end capacity is reduced by all these phenomena, these meteorological, orbit, etc. So we need to have a high-capacity satellite in order to provide useful services. And the approach taken here is to develop new quantum technology. So there's teams working in-house to develop high-rate quantum sources and detection modules. But it's also to exploit as far as possible the heritage developments that have already taken place. And here we can make use of some very, very important heritage developments in the field of classical laser communications. So there's already quite large diameter optical terminals which have been developed to allow uplink feeder links to geostationary satellites. And these can be customized and reused for this application. And then in order to simplify the pointing, because these have pointing mechanisms which were more designed to cover the Earth from geo, so not such a broad range, we couple this with Earth observation satellites, which are agile satellites. The whole satellite moves to point to the target. So that's the second heritage technology we employ for these developments. And we also employ the ground terminals, which we have an extensive range of ground terminals of different diameters in-house. So we put all this together, new developments, customized heritage developments to create a high throughput satellite. And I maybe should have pointed out the importance of the diameter of this telescope is because the width of the beam generated to Earth is inversely proportional to the diameter of a telescope. Broader the telescope, you create a much finer beam down to Earth, and this beam then enters another telescope on the ground, so the finer it is, the more probability of the photon falling on the telescope on the ground. So we need large aperture diameters on the telescope to relieve the ground stations and to allow to have smaller terminals on the ground. And our motto then is to not waste the photons. They're complicated to generate, and so we use large diameter optics to make sure we don't lose them en route. And just a couple of last slides. So this slide is just to remind, although it's not the focus of the talk, that we do also have this other thread. This is the thread of quantum information networks. So once more, we have the satellite at the heart of the story. This time it's about generating entangled photons. And then these photons are then used for connecting subnetworks of quantum computers and quantum sensors, or potentially even providing classical secure communications from classical devices, but in an entirely untrusted end-to-end fashion of the quantum internet. And there again, employing the method of quantum teleportation, where the quantum information unit, the qubit, enters one side. We use this resource of a shared entangled photon, and out the other side pops the same qubit that entered. So in summary, so we've been working closely with the European agencies, the European Commission and the European Space Agency, to develop an operational European Euro QCI. We've designed a high-capacity satellite solution leveraging the heritage solutions of Airbus. And we're currently developing the space solutions to enable quantum cryptography and the quantum internet. So these are two streams which are very actively pursued. And our high-capacity products will bring quantum communication services to the end user. We target providing exploitable capacities that can be used for real-life applications. Thank you very much.
Yeah, thank you so much for the talk. Always interesting to see where the difference between post-quantum and quantum cryptography is. It's not just a word, there's a little bit more of a difference. Do we have any questions?
Yes. Thank you very much. My question was about, you show like the key rate, depending on the environment and other stuff. But how much do we need to send like the key each time we connect to the satellite? Couldn't we share like the same key for some orbits?
So, if I understand correctly, it's about the key volume that's requested.
Yeah, exactly.
So, we treat this as a data product. So at the moment, we try and be as agnostic as possible about what it's actually used for afterwards.
Okay.
So there will be maybe a key derivation function which is applied to it to use it for something. The best use that could be put to it is to use it once more for a one-time pad. That would preserve the ITS property end to end. But we implement an idea of segregation. We provide the key material, but we rest ignorant of how it's actually exploited at the end. This is what would be requested of our customers as well. Yeah.
Okay, so for now it's just like data rate, but for key like
yes.
in a way, and we'll see afterward how to change it like as a key and how much like the implementation.
Exactly, but so we don't really have a granularity like that. We're not talking about 256-bit blocks being developed, but there is an inherent granularity in the post-processing part.
Okay.
So this is a granularity of much longer blocks of key. This is simply because the post-processing is not a continuous process. It needs data blocks to be performed.
Okay, thank you very much.
Yeah, thank you. Very interesting. I have two questions actually. What is the timeline for you to launch actually a satellite, and what's the state of the art? Because I know that China tried to do this some years back. So what did they achieve?
Okay, so the timelines for both these streams is about 2030, maybe a little bit earlier for the entanglement source, because this will be more of a demonstrator mission, whereas The prepare and measure mission would be a precursor mission, allowing secure operations. So all the work is being performed in strict security conditions to make sure that we're not implementing any backdoors in the system, and so that's this time scale. The Chinese mission was called Misius, was launched in 2016, and this is an amazing mission. It was a real scientific accomplishment, what was implemented there, and technical accomplishment. This was not targeted as being a secure mission, however. I mean, it's more of a demonstrator mission. So I think at the current time, from the intelligence that we have, they are putting into place a guaranteed secure mission at the moment. But it must be said, there is a lead in China. They are ahead.
All right, we have a question online from Peter Franke. Are there approaches to eliminate the necessary trust in a satellite while still using prepare and measure?
Well, there are proposed solutions to this, but they always have been in the past shown to be incorrect, and that the justification has never been rigorously valid. So the current thinking in the area is that this cannot be made to disappear by using some sort of algorithmic approach. So things have been proposed, but nothing has really withstood scrutiny.
All right, thank you. Do we have any other questions? All right. If there are no more questions, thank you again for the talk.
Thank you very much.